So let's suppose that this satellite revolves around Earth in this circular orbit, and radius of this orbit is small r. Okay, so we know what is small r. Small r is equal to radius of Earth plus h. H is the height. Okay, h is the height above the Earth's surface. So now for this circular motion, some centripetal force will be required. So FCP is the centripetal force, and we know that it is provided by the gravitational force. Okay, so FCP is equal to what? It is G times m into m divided by r square. Then we can substitute the formula for the centripetal force. It is mv square upon r. So mv square upon r is equal to gmm divided by r square, and this r square, I mean this r will get cancelled out, so only r will be left on the other side, and m gets cancelled out. Okay, so we get v square equals to g times m over r, and that means v is equal to square root of that, square root of gm over r. Okay, square root of gm divided by r plus h, right? So this is the orbital speed of the satellite. Okay, this is the speed with which satellite will revolve around the Earth. Okay, so this is orbital speed. After that, we can substitute in place of this gm, gh multiplied by r plus h square. Okay, so we know that gm is equal to g into r square, or it is equal to gh multiplied by small r square. So if we substitute that, okay, if we substitute that, what do we get? We get another formula for the speed of satellite. So that is v equals to square root of g into r square, sorry, gh multiplied by r square divided by r. So it's equal to what? This r gets cancelled out with the square. So it's equal to gh multiplied by small r. Okay, or we can say gh multiplied by r plus h. So that is another formula for the speed of this satellite. Okay, so is it clear, or is there a question? So let's find out time period first, right? So time period of a satellite which revolves around Earth. Okay, so we got this formula for the speed, v equals to square root of gm divided by r. Okay, v equals to square root of gm divided by r, and then we can substitute for v as 2 pi r upon t. Okay, so v is equal to 2 pi r divided by t. This is speed in circular orbit. So it's equal to square root of g times m upon r. Now we'll square both sides. So what do we get? We get 4 pi square r square divided by t square. It's equal to what? Square root of gm upon r square is gm divided by r, right? Then we can rearrange this, and by rearranging this, what do we get? We get t square is equal to, we take that r on this side and gm also on this side. We will get t square is equal to 4 pi square, sorry, 4 pi square r cube divided by gm. Okay, t square equals to 4 pi square r cube divided by gm. Now 4 pi square is a constant, gm is constant, so therefore what we get is t square is directly proportional to r cube. Okay, so this is Kepler's third law, right? Square of the time period is directly proportional to cube of the radius. Okay, cube of the average distance, you can say. And then if you want, you can find out the formula for the time period by taking square root on both sides. Okay, so what do you get? If you take square root, you get t equals to square root of 4 pi square is 2 pi. Okay, square root of r cube upon gm. Okay, so this is the formula for time period of a satellite revolving around Earth. And if we want, we can substitute small r equals to capital R plus h everywhere. So then let's find out energy of a satellite. Okay, so let's find out energy of a satellite revolving around Earth in circular orbit. Okay, so now it will have two kinds of energies, right? The satellite will have two kinds of energies. So total energy of a satellite is addition of potential energy and kinetic energy. So potential energy plus kinetic energy. So now earlier we have studied the formula for potential energy, and it is minus of gmm divided by r. Okay, so if satellite is at distance small r away from the center of Earth, the formula for potential energy is minus of gmm divided by r. And kinetic energy, we know it is half of mv square. Okay, so kinetic energy is half of mv square, so it's equal to minus of gmm divided by r plus half of m multiplied by v square. And what is the speed of satellite? Speed of revolving satellite. So speed of revolving satellite, square root of gm over r. If we take its square, we'll get gm upon r, right? We get gm upon r. So it is gm divided by r. So here we have minus of gmm upon r plus half of gmm upon r. So result of addition of these two will be equal to what? Minus half of gmm upon r. So this is the total energy of a satellite. And you can see it's negative. So what does it mean by total energy is negative? So this negative sign indicates that satellite is bound with Earth. Okay, and if you want to make it free from Earth's gravitational influence, then you will have to provide that much energy. Okay, how much of energy? This much of energy. Okay, so total energy of a satellite is negative. Okay, now there is some relation between total energy, potential energy, and kinetic energy. Okay, so you can see the relation. So if you compare total energy and potential energy, so you can see the total energy is equal to half of potential energy. Okay, because total energy is minus half of gmm upon r, and potential energy is minus of gmm upon r, right? So total energy is half of potential energy. Okay, and what is relation between total energy and kinetic energy? So kinetic energy is half of gmm upon r. Total energy is minus half of gmm upon r. So total energy is equal to, it's equal to what? Minus of kinetic energy. Okay, because if you see, the formula for total energy is minus half gmm upon r, and formula for the kinetic energy of revolving satellite is half of gmm divided by r, right? So there is only difference of negative sign between the total energy and kinetic energy, and therefore you have total energy equals to minus of kinetic energy. So these are important relations. I mean, if you know the formula, you know the relation, right? But we have to know this. We have to keep this in mind. Okay. So we have seen that why total energy of a revolving satellite is negative. So this negative sign indicates that satellite is bound. Satellite is bound with the Earth's Earth's surface. Okay, sorry, satellite is bound with Earth, right? So this negative sign indicates that satellite is bound with Earth, and in order to make it free from Earth's gravitational influence, we need to provide this much energy. Okay, we need to provide this much energy. All right. So the energy which needs to be provided to any body to make it free from Earth's gravitational influence is known as binding energy. Okay, what is binding energy? This energy required to make any body free free from Earth's gravitational influence. From the Earth's gravitational influence. Okay. So for a revolving satellite, it's clear that this much energy, if we give this much energy, okay, that is half of gmm upon r, then the satellite will become free from Earth's gravitational influence, right? So binding energy for a revolving satellite is half of gmm upon r. And how do we give this energy? So if we give this much energy, the satellite will become free. So how do we give this energy? We give it in the form of kinetic energy, right? We provide some speed to the satellite. So it has already got some speed. Okay, it has already got some speed. How much? Square root of gm upon r. So this speed is known as critical speed. This speed is known as critical speed. Okay, the speed which has to be given to any body to make it free from Earth's gravitational influence, it is known as escape speed. Okay, it is known as the escape speed. So next we are going to find out how much is the speed required. Okay, so see, escape speed. Okay, so now binding energy is half of gmm upon r. So the extra kinetic energy that we are going to provide to a satellite to make it free, okay, it must be equal to what? It must be equal to this binding energy. So I will call it kinetic energy of escape. Kinetic energy of escape, it's equal to half of gmm divided by r. If we provide this much extra kinetic energy, then the satellite will become free. Okay, so kinetic energy of escape is half of m into ve square, and it's equal to half of gmm divided by r. Then this half and half gets cancelled, m and m gets cancelled. So what is left is v square is equal to gm upon r. So v square is equal to what? Gm upon r, and therefore ve is equal to square root of gm over r. Okay, so the critical velocity of a satellite. What is critical velocity? The velocity with which satellite revolves is known as critical velocity. Vc, it is square root of gm over r. And we have seen if we give same amount of extra speed, okay, so it has already got this much amount of speed. with which it is revolving around Earth. If we provide same amount of extra speed, what happens? It becomes free. Okay, it will escape to infinity, right? It will escape to infinity. Okay, so in case of revolving satellite, in case of a revolving satellite, we get that the escape velocity is just equal to its velocity. Okay, the velocity with which it is revolving around the Earth's surface, around the Earth. So is this thing clear? Now let us find out escape speed for a body which is on the Earth's surface. Okay, so there is anybody, okay, whom you don't like, and you want to throw that person or that body, and you want that person to never come back. So with how much speed you must throw that person so that it will never come back. Okay, so let's find out that. So escape speed, we want to find out escape speed for a body or a satellite resting on Earth's surface, resting on Earth's surface. Okay. So first of all, the body is resting on Earth's surface. It has got no kinetic energy, right? So for that body, total energy is just equal to what? It is just equal to potential energy. Okay, or we can say it's equal to potential energy plus kinetic energy. But since the body is resting on Earth's surface, its kinetic energy is zero, right? So since kinetic energy is zero, we have total energy equals to potential energy. And potential energy for a body on Earth's surface is gmm divided by capital R. So the total energy of body resting on Earth's surface is minus of gmm upon capital R. Okay. So what would be the binding energy? Binding energy is just negative of total energy. So if we provide this much energy, what will happen? The body will escape from Earth's gravitational influence. Okay, so binding energy is gmm divided by R, right? And therefore we can say that the kinetic energy of escape is equal to, it is equal to binding energy, and that is gmm upon R. Okay, so now let's substitute kinetic energy equals to half of m into v square. Okay, so that is half of m into v square is equal to gmm divided by R. So this m and m gets cancelled. Take 2 on the other side. So you get v square. V square is equal to what? 2 times g multiplied by m upon R. So v equals to square root of 2gm upon R. Okay, v is equal to square root of 2gm upon R, right? So now if you compare this with the critical velocity of satellite revolving around Earth's surface. So how much is critical velocity? It is square root of gm upon R plus h. So if satellite is revolving very close, okay, very close to the Earth's surface, then v is just equal to what? Or vc will be equal to square root of gm upon R. So v is equal to V is equal to what? It is just equal to square root of 2 times VC. Let's talk about geostationary satellites. So what is geostationary satellite? It's a satellite which remains stationary with respect to the Earth. Okay. So what would that mean? So now let's suppose this is Earth, and you have some satellite revolving around Earth. Okay. So let's redraw the Earth. Let's suppose this is Earth and there is some satellite over here. Okay. Which is revolving around Earth. Now you want this satellite to be fixed with respect to Earth. Now it is, so if you see from this position, if there is some person standing over here, the satellite will be over the head of that person, right? So if you draw a perpendicular from that satellite to the center of Earth, or if you draw a line joining center of Earth to the center of that satellite, it will pass through the head of this person. Okay, and the satellite revolves in such a way that it remains there itself. It remains fixed with respect to this position. Okay, this position on Earth. Okay, I'm sorry. So the satellite revolves in such a way that it remains fixed with respect to the Earth, and that's why it is known as geostationary satellite. So now, which thing must be true such that the satellite is geostationary? Okay. So let me ask it in this way: how much should be the time period of a geostationary satellite? Must be 24 hours, right? It must be 24 hours. So see, this is suppose North and South Pole, right? This is North Pole and South Pole. So Earth rotates about this North and South Pole, about the axis passing through North and South Pole, okay? And it completes one rotation in 24 hours. So if you want a satellite to be fixed with respect to some position on Earth, it must revolve and it must complete one revolution in 24 hours. Okay. So if Earth rotates with some angle, that satellite will revolve with same amount of angle, right? And if it is above some position, it will remain at that position only. Okay. So what must be the position of this geostationary satellite? It must revolve in this equatorial plane. Okay, it must revolve in the equatorial plane. So this is your satellite. Now it's a little bit difficult for me to draw it. Suppose it remains fixed with respect to uh, if I join this center of Earth and center of satellite. So with respect to this position, then Earth rotates, okay, with some angle. That satellite must rotate or must move with same angle, right, in same amount of time. Okay, so in order to in order to that thing to happen, T must be equal to what? 24 hours. Time period of geostationary satellite is 24 hours. Okay, and now we know the time period, so we can find out height of geostationary satellite, because we have got relation between the time period and the height. We know T equals to 2 pi multiplied by square root of r cube upon gm. Okay, so it is 2 pi and the small r is equal to capital R plus h. So it is capital R plus h cube upon gm, and then you have t on this side, right? So now if you substitute t equals to 24 hours, so it is 24 multiplied by 3600, then you have r equals to 6400 kilometers. Okay, 6400 kilometers. And then you know g, you know capital M, so h is only unknown. Okay, h is only unknown, and if you substitute all those things, you can find out h. So what does this mean is this geostationary satellite cannot revolve at any height, right? It will have fixed height. Okay, it will have fixed height above the earth's surface. Yes, no? So let us solve some problems based upon these things. Time period of a geostationary satellite is 24 hours. At a height 6 RE, RE is radius of Earth, from the surface of Earth. Time period of another satellite whose height is 2.5 RE from the surface will be. So they have given the time period of geostationary satellite is, it is 24 hours, we know that, and its height is 6 times RE. So T2 square is directly proportional to R2 cube, and T1 square is directly proportional to R1 cube. So now if we divide this first expression by the second expression, what can we say? We can say that T2 upon T1 square is equal to R2 upon R1 cube. Okay, so this is equal to what? R2 is 2.5 RE. We can substitute that 2.5 RE upon 6 RE. R1 is 6 RE, and we have cube of that. Okay, so this is T2 upon T1 square. Then RE and RE gets cancelled out. Okay, so the thing that I have done wrong is this is the height of our Earth's surface. Okay, this is the height above the Earth's surface, and this is not the actual radius. So we know small r is equal to capital R plus h. Okay, so I thought it is actual radius. Okay, so I'm sorry. Yeah, so then it's simple. So it is 6 times of RE is the height. 6 times of RE is the height. So how much is the actual radius? So it is R plus H, right? So it is RE plus 6 RE. Okay. Radius of first one is RE plus 6 RE, and radius for the second one is RE plus 2.5 times RE, and you have cube of that. Okay. So it is RE plus 2.5 RE is 3.5 RE, 3.5 RE, and in denominator you have 6 plus 1 RE, that is 7 RE, and then you have cube of that. This is T2 by T1 square. Okay, so this RE and RE gets cancelled out. Then 3.5 upon 7 is 1 by 2. So you have 1 by 2 cube. Now you can take square root on both sides. So 1 by 2 cube is 1 by 8. And if you take square root, because this is T2 upon T1 square, so if you take square root, it will be how much? So it is 2 root 2. That's T2 upon T1. Now take T1 on other side. So you get T2 equals to T1 divided by 2 root 2. Okay. And T1 is how much? It is 24 hours. So it is 24 divided by 2 root 2 or 12 upon root 2, or you can say it is 6 root 2. Okay, so 6 root 2 is the answer, right? A remote sensing satellite of Earth revolves in a circular orbit at a height of 0.25 multiplied by 10 raised to 6 meters above the surface of Earth. If Earth's radius is 6.38 multiplied by 10 raised to 6 meters and g equals to 9.8 meters per second square, then the orbital speed of satellite is. So we know the formula for orbital speed of satellite. Okay, so v equals to square root of gm upon r, that is square root of gm upon r plus h. Small r is capital R plus h, and you are given that height is this much, then Earth's radius is this much, okay, and small g, g is equal to 9.8 meters per second square. So now what we can do is we can convert this gm in terms of g, right? So what do we get? The g r square divided by r plus h, and now there will be a lot of calculation in this, but we can solve it. So it is 9.8 multiplied by r square. So how much is r? R is 6.4. Okay, let's do round figure. 6.4 into 10 raised to 6. So 6.4 multiplied by 10 raised to 6, and there is square of that, divided by r plus h. So r plus h is 6.4 multiplied by 10 raised to 6, and h is 0.25 into 10 raised to 6. Okay, so plus 0.25 multiplied by 10 raised to 6. Okay, so we have r square, and square root of that will not touch this thing. We'll just take it outside. Okay, so what do we get? We get 6.4 into 10 raised to 6 multiplied by square root of 9.8, and in denominator what do we have? We have 10 raised to 6, right? Square root of that is 10 raised to 3, so we can take it outside, and then 6.4 plus 0.25, so it is how much? 6.65. Okay, so 10 raised to 6 upon 10 raised to 3 is 10 raised to 3, and 9.8 divided by 6.65 will be, we can say round figure, it will be how much? This is 3 is to 2. Okay, near about 1.5 or something. So square root of that will be nearly, we can say 1.2. Okay, and if I am correct, so this will be greater than, yeah, it will be greater than 6.6. So I guess this will be the answer. Okay, can you check? So let's move on to the next question. Satellite S is moving in an elliptical orbit around the Earth. The mass of satellite is very small compared to mass of Earth. Then A, the linear momentum of S remains constant in magnitude. B, the acceleration of S is always directed towards the center of Earth. The angular momentum of S about the center of Earth changes in direction, but its magnitude remains constant. The total mechanical energy of S varies periodically with time. So which one is correct out of this? This is simple. There is a satellite S which is moving in elliptical orbit. Okay, so does the linear momentum of S remains constant in magnitude? So linear momentum is mass times velocity. No, very good. Because velocity changes. Okay, so if it is revolving in an elliptical orbit. So velocity is more when the satellite is closer to the Earth, and velocity will be less when it is away from Earth, right? So since velocity changes, linear momentum is not constant in magnitude. The acceleration of S is always directed towards the center of Earth. This is true. Okay, so this should be the answer. But let's check the remaining two. Okay, the angular momentum of S about the center of Earth changes in direction, but its magnitude remains constant. So this is wrong because the angular momentum will remain constant in magnitude also. Okay, so we had discussed this when we discussed Kepler's laws. So there is second law. So law of areas. Okay, so law of areas is law of conservation of angular momentum actually. Okay, so angular momentum remains not only constant in magnitude, it remains constant in direction also, because it is under the action of a central force. So we had discussed this when we discussed the Kepler's laws. So angular momentum remains constant in magnitude as well as direction. So this is wrong, and total mechanical energy varies periodically with time. So again this is wrong. So will the total mechanical energy vary? Total mechanical energy will remain constant because there is no external force, right? So if it moves away, speed will decrease. Okay, its speed decreases, that means the kinetic energy will decrease. But what will happen? Its potential energy will increase. How? Because potential energy is what? Minus of gmm upon r plus h is the potential energy. That means as height increases, what will happen? This fraction will decrease, but it has got this negative sign. Okay, so it was more negative earlier, now it is becoming less negative, right? Fraction decreases, that means when it is closer, it was more negative, but when it goes away, it becomes less negative. That means the potential energy is actually increasing. Okay, so this one is also not true. The total energy remains constant, right? So option B is the answer. Let us see next question. A geostationary satellite is orbiting Earth at a height of 5r. That means its radius is r plus 5r, right? R plus h. Okay, so let's keep this in mind. Above the surface of Earth, r being the radius of Earth, time period of another satellite in hours at height of 2r from the surface of Earth is. Okay, so again this is simple. Okay, and I think the answer would be same. Right? See, so for first one, so T1 is equal to 24 hours. Okay, so we can say T2 upon T1 square is equal to R2 upon R1 cube. Okay, so R2 is equal to what? It is R plus 5R because height is 5R. So it is 6R. And R1 is how much? It is R plus 2R because height is 2R. Okay, so it is 3R. Actually the other way around, because R2 is, okay, R2 is 3R and R1 is 6R. Okay, so height of first one is 5R. So R1 is R plus 5R and R2 is R plus 2R, that is 3R. Okay, so then we have got 1 by 2 cube, and so this is just like the previous question. So 1 by 2 cube is 1 by 8, so it is T2 by T1 square. So therefore T2 upon T1 square root of this, right? And therefore T2 is equal to what? T1 multiplied by square root of this thing. So square root of 1 by 8 is 1 upon 2 root 2, and T1 is 24 hours. Okay, so they have just changed the values, but it is same question. So 24 upon 2 root 2. 24 upon 2 is 12. 12 upon root 2 is 6 root 2. Right, 6 root 2 hours. So option C is the answer. If V is the escape velocity and VO is the sorry, if V is the escape velocity and VO is the orbital velocity of a satellite for orbit close to Earth's surface, then these are related by. So tell me, VO equals to root 2 VE, VO equals to VE, V equals to root 2 V naught, or V equals to root 2 times VO, VO or V naught. Option C or D. Option D, right? Option D is the answer. Okay, all right. Then the radii of circular orbits of two satellites A and B of the Earth are 4r and r respectively. If the speed of satellite A is 3v, then the speed of satellite B will be. So again, this is okay. They have asked same type of questions again and again. Okay, the radii of circular orbits of two satellites are 3r and r respectively. Okay, so let's say r1 is equal to 4r and r2 is equal to r, and we know the formula for speed. So speed is what? V equals to square root of gm over r. Okay, so v1 will be equal to square root of gm upon r1. So you solved it, very good. So v1 is square root of gm upon r1, v2 will be square root of gm upon r2, and dividing by that is equal to what? Multiplied by its reciprocal. So multiplying by r2 upon gm. So gm and gm will get cancelled out. Okay, so v1 upon v2 equals to what? Square root of r2 upon r1. So that is r2 is r, r1 is 4r, r and r gets cancelled. v1 upon v2 is square root of 1 by 4, that is 1 by 2. Okay, that means v2 equals to 2 times v1, right? v2 equals to 2 times v1, and therefore v1 is 3v, so it is 6 times v. So option B is the answer. Let's see next question. A ball is dropped from a space sorry, a ball is dropped from a spacecraft. Okay, it is tongue twister. The ball is dropped from a spacecraft revolving around the Earth at a height of 120 km. What will happen to the ball? So there is a spacecraft which is revolving around the Earth at some height, and you drop a ball from that height. What will happen? It will fall down to the Earth gradually. It will go very far in the space. It will continue to move with the same speed along the original orbit of spacecraft. It will move with the same speed tangentially to the spacecraft. Tell me, ball and spacecraft both have same speed, right? And you are just releasing that ball. Okay, so it has natural tendency. This is Newton's first law. Okay, so it was moving in circular orbit earlier. So it is inside or outside of that spacecraft. It has got same speed. Okay, and because of that it will keep on moving with the same speed in same orbit, right? So this is an example of Newton's first law. Okay, right. Okay, so let's see next question. A satellite A of mass m is at a distance r from the center of Earth. Another satellite B of mass 2m is at distance 2r from Earth's center. Their time periods are in the ratio of. Okay, so what are the ratios of time periods? So ratios of radii are 1 is to 2. So we know T1 by T2 square equals to R1 by R2 cube, or we can say if we take square roots, so it is R1 by R2 raised to 3 by 2, right? So it is 1 by 2 raised to 3 by 2, 1 by 2 raised to 3 by 2, or it is 1 by 2 cube, which is 1 by 8, square root of that. So square root of 1 by 8, that is 1 upon 2 root 2. Okay, so it is 1 upon 2 root 2. So option D is the answer. Very simple. What about the mass? It doesn't depend on mass, right? Mass is there to confuse you. Okay. So see, formula for time period is 2 pi square root of r cube divided by gm. And this mass is not mass of satellite. Okay. This is mass of Earth. So time period doesn't depend on mass of satellite. It depends on mass of Earth. Okay. So it doesn't matter how much is the mass of satellite. Okay. It does not depend on mass. All right. So let's move on to the next question. A satellite of mass small m is orbiting the Earth of radius capital R at a height h from its surface. Total energy of the satellite in terms of GO, the value of acceleration due to gravity at the Earth's surface is. All right. So we know the formula for total energy. How much is total energy? It is minus half of GMM upon small r. And what is small r? It is r plus h, right? And they're asking how much is total energy in terms of GO. GO is the value of acceleration due to gravity at the Earth's surface. So now we have discussed this repeatedly. The trick to solve gravitational problems, most of the problems, is use GM. Remember this thing, GM is equal to what? G multiplied by R square. So here they are calling it G suffix O, GO or G naught, and it is equal to GH multiplied by R plus H square. Okay, so out of these two, this one is what we have to use because they are asking it in terms of acceleration due to gravity on Earth's surface. Okay, it is minus half of GM is GO multiplied by R square into M divided by R plus H. So in place of GM, I am substituting this. So is it matching with something? Any option? I guess option B, M G naught R square. Yes, it's option B. Right. So this is also simple. Okay. Next question. The additional kinetic energy to be provided to a satellite of mass m revolving around planet of mass capital M to transfer it from circular orbit of radius r1 to another of radius r2 where R2 is greater than R1 is. Okay, so now how can you find out that energy? So it's simple. See, there will be some total energy of satellite at uh, radius R1. So let's call it total energy at R1, or let's just call it total energy 1. Okay, it will be simple that way. So it is minus of GMM divided by R1. Then when it goes to the next height, okay, R2, sorry, the other radius R2, it will have total energy equal to what? Minus GMM divided by R2. So now the difference between these two total energies will be equal to the extra kinetic energy that has to be provided, right? So it has got total energy, some energy, okay, some energy now when it is revolving at radius r1. It will have some energy, some total energy when it revolves at radius r2. So the difference between these two energies is the extra kinetic energy that you have to give. Yes or no? So how much is the extra kinetic energy? It is final total energy minus initial total energy. So it is minus of GMM upon R2. This is final total energy minus of GMM upon R1. So this minus minus, this thing becomes plus. So you can say, you can take GMM common, and this one becomes positive. So you can write it as 1 upon R1 minus 1 upon R2. Okay, so option B is the answer. Next question. Two satellites of Earth S1 and S2 are moving in same orbit. The mass of S1 is 4 times the mass of S2. Which one of the following statements is true? The potential energies of uh, Earth and satellite in the two cases are equal. So this is not true because potential energy depends on mass. It is minus of GMM upon R. It depends on mass of the satellite. Okay, so Sanjay is saying option B. Let's check. S1 and S2 are moving with the same speed. This must be true because they are moving in same orbit, right? So yes, this is true. Option B. Okay. So then the kinetic energies of two satellites are equal. So kinetic energies of two satellites cannot be equal because their masses are not equal. Okay, their masses are different. Okay. So speed is same, but kinetic energy is half of m into v square. So it depends on mass. Speed is same, but mass is different. So kinetic energies are different. Time period of S1 is 4 times that of S2. So we have discussed this earlier. The time period does not depend on mass of the satellite. Okay, it is independent of mass. So this is also wrong. So option B is true. Okay, option B is correct. For a satellite moving in an orbit around the Earth, the ratio of kinetic energy to potential energy is. So what is the ratio of kinetic energy to potential energy? So this is very simple. We have discussed this. Tell me. Kinetic energy is half of GMM upon R. Potential energy is minus of GMM upon R. If you take the ratio, you will get KE upon P equals to minus half. And if you just want the magnitude, then it is half. Option A. Right. So earlier you said C. Okay. Anyways, so A is the answer, right? Okay. Next question. The satellite of mass m is moving around the Earth in circular orbit with velocity v. What will be its total energy? So we know that total energy is equal to minus of kinetic energy, right? We know total energy is minus of kinetic energy. It is minus of half mv square. Option D. Okay, so this is simple. So see, now we have to memorize these things. What is the relation between total energy, potential energy, kinetic energy, and binding energy? Okay. Next question. The mean radius of Earth is r. Its angular speed on its own axis is omega, and the acceleration due to gravity at Earth's surface is g. What will be the radius of orbit of a geostationary satellite? Okay, so angular speed of Earth is omega and acceleration due to gravity on Earth's surface is g. What will be the radius of orbit of geostationary satellite? This is the question. Okay, so let's suppose radius is small r. Okay, so now uh, okay, so now what can we say that okay, for revolution of satellite the centripetal force is provided by the gravitational force, right? So FCP is equal to GMM upon r square. Mean radius of Earth is r. The angular speed on own axis is omega, and uh, yeah, so we can use this formula, right? So then, what is FCP? The centripetal force. It is mv square upon r, or we actually omega is given, so we should use m r omega square is gmm divided by r square, right? Okay, and then this m and m gets cancelled out, so we get r cube is equal to gm divided by omega square. Okay, and therefore r is equal to square root of, sorry, cube root of this thing, gm upon omega square. Okay, and then we can substitute in place of gm or regular trick. So gm is equal to what? Gr square. Okay, so if you substitute that, gr square upon omega square, I'm sorry, so here it's cube root of this, right? Okay, so I have put the bracket, but I didn't take cube root. So r cube is gm upon omega square. R is equal to what? Cube root of that. Okay, so you have gr square upon omega square and cube root of that. Okay, so it's option A, option A or option B? Option A, right? In option B, it is R only. Here we have square. So is it clear? Okay, good. Then, yeah, this was the last question. Okay, so this one, yeah, I think Only this question was little bit good. All other questions are easy, right? And most important thing in gravitation, you can you can see this. So this thing is one of the most important thing. You have to remember gm is equal to gr square. Okay. So any question